Today we're going to be looking at this particularly difficult and interesting GCSE differentiation problem. So we're talking about a curve which has got a quadratic formula and you want to know something about maybe its turning points. Now this doesn't seem particularly strange, but then when you look at this more carefully, you see that one of the coefficients is given to you algebraically. Okay, it could take on more than one role. So we're not talking about any particular equation and its turning points, we're talking about like a whole class. So let's answer the first part, which is generally quite straightforward. Show that when k equals 0, you got to find the turning point. All right, so dy by dx is going to be equal to the derivative of the whole thing when when k is 0. So it becomes quite straightforward, which is just equal to 4x. And then you want to know when this is 0. So you get 4x equals 0, x equals 0. Put that back into the original one, and you're going to get y equals -3. Now, that's not particularly difficult, but show that when k is not equal to 0, the turning point on C must have negative x coordinates. Well, let's try to think about what this looks like, and I think a good way to do it is graphically, so I'm going to put it into Geogebra. I'm going to plot loads of possible values of k, and then you'll see how the turning point is always negative, and then we'll try to justify this algebraically. And then I'm going to put k in here, and then as you can see, I can actually vary k. And this shows you what we're trying to work out. We're trying to work out something about every single one of these equations, which is really, really quite different from most GCSE questions where you're expected just to work out a single one, okay? So as you can see, all these equations are different, but they form some sort of pattern. You can see there's some region. So that's what we want to try to understand. All right, welcome back. Now, let's just differentiate this. Even though we don't know what k is, because it could take on infinite number of values, it's still just a constant in each case. So when you differentiate this, you're going to get 4x plus akx. Now, when this equals 0, we can differentiate this slightly. We can simplify it. We can divide by 4, and we get this plus 2k squared equals 0. And there's a few ways to think about this, but probably the easiest one is just to make x a subject and think, okay, well, k squared has to be either positive or negative. And whenever you square it, you're going to get positive, and then you're going to multiply it by -2. So x has always got to be negative because it's the negative of a non-zero square. And now when k does not equal 0, determine whether or not the y coordinate of the turning point is negative. So this is more interesting. Let's think, okay, if x becomes -2k, we can actually substitute that back into the original equation. So let me just do this. So let's take the original equation again, 2x squared plus 8k squared x -3, and we're going to replace x with -2k squared because that's what we found earlier. So you're going to get equals 2 times -2k squared. Got to keep track of those squares. 8k squared times by -2k squared -3. Well, let's have a look. This one is going to be 8k to the 4. Plus, minus 16k to the 4 -3, which simplifies tremendously to minus 8k to the 4 -3. Now, we know that k to the 4 is always going to be a positive number, which means that -8 times it must always be a negative. And negative take away 3 is still negative. So we know that all of the y coordinates are also going to be negative. And that's kind of what we saw, right, when you saw the plot. You saw that all the turning points were like this, okay? They all had negative y values. So that's how we do it.